Today we are going to be talking about how we made PHP extremely fast. We are going to be analyzing what the strategies we did and how close we got to native, if any close. So let's start with who are we speaking today. Here is Edo, here is myself. Here is images generated by ChatGPT with the latest trending trend in X, which was making the images with Ghibli. And yeah, we both work at Wasm. If any one of you don't know, the name of Wasm actually came from Wasm and Docker, so that just by itself is hopefully very cool. And yeah, we've been working on making things extremely fast. So to make WebAssembly be approachable and usable by a lot of companies and use cases, we actually need to make it run almost as at native speeds, because otherwise it's going to be not compelling for some of the use cases that we are working at Wasm. So about 1 year ago, we presented the first strategy, which was to make Python faster. And we got it working with kind of like pre-compiler using Nutka. We presented here 1 year ago, and TLDR, we made it like 3x faster. It was still about like 20% slower than native, but it was like noticeably faster, especially like versus a normal interpreter. So after presenting this, and about 6 months later, we started working on Wasm Edge, which is basically a platform to run compute on the edge or on the clouds. And we scale things automatically and so on. So we want to bring more workloads into the edge. And one of the most non-sexy workloads is actually WordPress. And probably like not all of us are attracted to PHP and so on. But the market is very huge. Actually, like around, I think 60% or 55% of all the websites in the world are running through WordPress. So it's incredibly a big use case. And all the hosting providers that exist on WordPress are actually like, let's say, not great. So we think we can make a difference here, and we started to see if we could actually run WordPress at the edge, and what will be the consequences of doing that, if we run at proper speed or not. So we started by just trying WordPress, and we started with our default backend, which was screen-lift, and with Async-5. I'm going to go in depth about why we use each of these things and why each of these things are going to be needed. But basically, when we tried to get WordPress working, it was taking a little bit to load. And after a little bit of time, basically, like the website load. More or less, the loading time was around 600 milliseconds. So this is not ideal if you want to make use of WordPress in production. This is about like 10 to 11x slower than native. So we cannot ship this to customers. Like basically, we ship that, no one will use us. So this was not a good enough strategy that we could do to actually like ship on production. We actually shipped this on production, by the way, but the speeds were not good. So we wanted to prove them. So why PHP was so slow? First, we started analyzing like what were all the reasons. First, is it didn't have OP cache. Second, we used screen-lift. And third, we use Async-5 for long jump and set jump. I'm going to go in detail about like each of those. So yeah, we're going to see about each of these cases, like what we did and how we enabled it. So let's start with OP cache. OP cache, for those that you don't know about PHP, is a strategy that PHP uses to cache all the parsing that it does on the files. And also, it does improve a little bit the speed times by doing small optimizations on that AST that it generates. So when you just run the homepage of WordPress, there are 350 files that are being parsed each time. So that more or less is kind of like what brings a lot of like a slowdown into WordPress. And there was one challenge that we face here, which is normally like PHP modules are run by using DLOpen and DLSyn. Basically, our native modules that like you can like integrate on the side. So we have to embed it inside of the same PHP binary, because right now, currently, WASIX doesn't support DLOpen and DLSyn, although we are working on that. So that's going to be actually pretty cool to see super soon. We have a prototype already. So yeah, basically enabling could be a huge win. So as you see, our sloth is going a little bit faster. We've gone from 600 milliseconds to around 380. So on about 1.5 to 2x speed up. So that was a great, nice win, but we are still far from production. We wanted to get into like way faster speeds, and we were still like about like 7x slower than native. So we look at the next strategy. Can we use other compiler? And I'm not sure if you have used CraneLift, but for some reason, in the last years, it actually have gotten slower on the runtime speed. I think they did a lot of refactors. I mean, the team is pretty smart, actually. Like, we'll find, you could probably like chat with them in this conference. A lot of them are here. But basically, like, LLVM has actually a lot of optimizations that we can use that are not available in CraneLift. This basically makes LLVM way faster on certain workloads than CraneLift. So how faster? More or less 2.5 to 3x speed up. This, by the way, I'm going to demonstrate everything, or we are going to demonstrate everything with demos. So you can actually run this yourself on your laptops if you have Wasm installed. By the way, the timings on Wasm CraneLift and Wasm time CraneLift, Wasm is a tiny bit smaller, faster. But basically, like, it's they are on par. So it's not that Wasm is emitting weird CraneLift IR. It's more about like CraneLift optimizations and so on. So by using LLVM, we got much nicer speeds. And the last one is that we are using Asyncify for long jump and set jump. So let's start with what the fuck is Asyncify? I'm just going to ask the question because I'm curious. Have any of you heard of Asyncify before? OK, more or less 1/3 of the room to a half. So Asyncify, in a nutshell, brings pause and resume to WebAssembly workloads. Why this is useful? Because when you do long jump and set jump, basically what you are doing is you're telling to the runtime to stop the program at that moment, or to save a checkpoint of where the program is at that moment. And then you might want to recover the program from that exact spot some moments later. Maybe 1 second later, 5 seconds later, or whatever. And basically, Asyncify transforms your WebAssembly code. So it introduces a lot of like checkpoints into your code, and make it possible to then like save the state and restore your program from the same state that it was running before. So that's how we were running long jump, or how we were enabling like long jump and set jump. This is not the strategy that we started. Actually, like, this strategy was created by Ruby Ruby into WebAssembly about 2 to 3 years ago. So yeah, we were using that. It was great. And basically, like, after you run Asyncify on a WebAssembly module, you will get an output .wasm. That is more or less about 1.5 times bigger. And the downside is 2 times slower. So yeah, we were like, what can we do to actually like get into more reasonable speeds? And the answer was use WebAssembly exceptions. WebAssembly exceptions prevented us to use Asyncify, and it allowed us to use long jump and set jump through WebAssembly exceptions. And as Edo is going to present in just 1 slide or 2, basically, like, we are going to see how they had like 0 cost and so on. So by having WebAssembly exceptions, we bring down the time about like 2x. So we ended with a 60 millisecond time of response for WordPress, which is quite fast. Here we can see our sloth now is in a Ferrari, very, very happy about like this new path. And right now, to go in a little bit more depth of WebAssembly exceptions, now Edo is going to present.
Yep. Hello. Hi again. And in this part of the talk, I'll try to give an introduction to how Wasm exceptions work. It will not be really in-depth, because it will take a day to explain it exactly. I didn't even understand it fully as of now. But so the proposal itself comes in 2 flavors. One is the legacy one, and the new one is the XNRef flavor, and we implemented this last one. In nature, it resembles the behavior of C++, the way C++ exception work. And in practice, it adds 2 new types, tag and XNRef, and the number of control flow instructions to throw and catch exceptions. As you can see here, although some of these embedders we can see in the WebAssembly.org features website and the page, it's gaining momentum, but it's not that widely adopted. And 3 out of the 5 that implemented are based on V8. So only V8 has it as of now, and Wasm 2C and Safari. So let's start slow. In the beginning, there was the module. After the module came the tag, and the tag pretty much is a way to represent an event that will happen in the code. As of now, tags can only represent exceptions, but in the future, the plan is that of having tags represent other kind of events. After the tag came the function that throws. And in this simple function, it just takes a parameter, checks if the parameter is equal to 0. If it is, then you're out. We throw an exception, and if it's not, then does nothing. And then we have a function that takes a parameter, calls this function, and tries to catch the exception that might be thrown by the check non-zero function. So what are the semantics of this statement, of this function? When we get into the block, we see the try table, and catch all is pretty much a statement that says whatever exception you might see being thrown, you catch it, and you return to execution after the block H. So if we catch an exception, execution will start back. Let's see if the pointer works. Yeah, here, after this block. It will basically return 1 if we catch an exception, return 0 if no exception is being caught. And this pretty much translates roughly to this C++ code. You can see, where is it? OK. You call this function, if the value is 0, you throw the exception, you catch the exception, return 1, no exception was caught, you return 0, and this is pretty much it. And let's get a bit more into the depth of how it works. It is a zero-cost abstraction, this flavor of exception handling, in the sense that if the function you have do not throw an exception, you don't pay a overhead to have them in your runtime or in the object file. So yeah, if you don't throw exception, you don't see any, you don't pay any cost during execution. It is based on the same structure that Wolf uses. That is, it's based on sections embedded in the object file. And as C++-like exception handling mechanism work, you need a cooperation between the runtime, the object format that you emit compiled functions in, and libraries such as lib-unwind. So how does it actually work? It's just a couple steps, nothing crazy. It is indeed a bit of an obscure corner of runtimes, and shout out to Nico Bailovsky, whose blog post pretty much formed the only introductory material for runtime embedders to implement exception handling. And yeah, in short, just 1 or 2 points. You have a function that I do, yes. I compile the function into an object. This already arguable. This object file has an EH frame. I said 3 points. Why there is so much white left in this slide. The EH frame section shall contain 1 or more call frame information records. OK. How many bullets? How many bullets? Oh no. Oh no. Oh no. Nah. Too long. Too long. Nah. Well, you see the joke again. OK, so let's start from the other way around, and of course, take it with not a pinch of salt, but a wheelbarrow's worth of salt. So you execute your code, you throw an exception at some program counter, let's say PC, and the runtime creates an exception object, let's call it E, and it encodes the type of the exception and the domain the exception belongs to. So for example, if you embed a C++ function that throws an exception in a Rust code base through FFI, Rust knows that the exception thrown by C++ is not a Rust exception, so it knows it's a foreign exception and treats it in a different manner. And yeah, so the runtime then calls lib-unwind, and lib-unwind does all the magic for us to look at the stack and see In the object file, you have sections that map program counters to catch blocks, roughly. And libanwind pretty much tries to see if the function the PC belongs to has a special function, which is called the personality function, calls this function, and these functions try to give to libanwind a way to figure out where to restore execution from. Basically, it just tries to find the catch block that belongs to the exception. If you if libanwind or the personality function together can find the catch block, then you're all set and execution can be restored. You need to manually install the context and restore the contents of the registers before you can actually return back to the catch block. You install the context, and if you don't find a catch block, control returns to libanwind, which gets to the parent function of the current function and tries to repeat the process. Of course, this means that you need to, unwind the stack, and if you don't find any function that can handle this exception, you're out of luck, and libanwind will be glad to inform you that, there's something wrong. No one caught the exception. And so, now, we perfectly understood how it works, and how this is from the theoretical side of things. Now, in practice, we need a runtime that actually supports EH-backed exception handling. So the steps towards that are to implement EH-backed setJump and lockJump in wasm, which, by the way, just uses an intrinsic function LLVM, which is Wasm setJump and Wasm longjump, I think, if I remember correctly. Then we compile PHP targeting this wasm, and we just have to find a runtime which we can use that supports the XMRF proposal. And V8 does indeed support it, and Wasm supports V8. So you can see here in this figure, we have this anecdotal, so to speak, does not really have a statistical balance, but it's just a rule of thumb of the execution speed. And you can see here, where is it? This is this benchmark run with V8 with normal non-EH-backed PHP. You can see it's almost 6.7 seconds. And with exception handling, it is 4.7, which is already great. But yeah, we had the support for V8 and exception handling in Wasm, but can we actually make it even faster? And here comes LLVM. We not only have V8, of course, we also have a backend based on LLVM. And roughly, the idea is that we get the WebAssembly, which is from it to LLVM IR, and then we compile it to native, apply the relocations, mark the code as executable, and all of that. And LLVM has this nifty landing pad intrinsic, which is used exactly to represent a C++ style exception handling. And we map the operations from the Wasm side to operations to the LLVM side. And we only have to create intrinsics in the VM, in Wasm, in the runtime itself, to allocate, destroy, throw, and rethrow exceptions. We must create our very own Wasm personality function. We mark each LLVM function we generate with that personality function, and yeah, profit. And I guess it's now time for the live demo. I shall only run use arrows and enter, so nothing can go wrong, right? Let's start with where we started from. Oh.
Here we go.
So these were the numbers we were seeing with crane lift before this whole endeavor. Okay, let's go. Good, but not great. Let's. Do we have LLVM without EH? I don't think so. So let's just cut straight to the chase and LLVM with EH. And yeah, I guess that's it.
Native.
Oh yeah, native. We are not actually done yet in the sense that we are close, but not exactly as fast as native. But still, with where we started from, I think these are great numbers. Of course, again, these are I don't think they really have a statistical balance in the sense that we then have to see how it behaves actually in production. But really, for a rule of thumb measurement, this is already great numbers. And yeah, back to you, Syrus.
Cool. So as we can see, or we have seen, with LVM, Wasm was able to run PHP just about 15% slower than native, which is quite good. We can, by the way, we are still experimenting with a few things that we believe is going to bring us way closer to native, and maybe in some cases even faster, which is fun to see. Yeah, we still have work to do, but we are getting much closer to where we want it to be. So now that we get the runtime fast, then we realized that boot time was slow. And why boot time were slow? Because WordPress actually parses 350 files at the startup. These, even when you OP cache, there are still some operations that you need to do. And there is a lot of initialization system calls that WordPress needs to do in order to render the homepage. So we were seeing about 1.2 seconds of cold starts. This is, by the way, this is just WordPress. Don't take on account any Wasm whatsoever. So if you try to run WordPress on Google Cloud, if you try to run it on Fly.io, if you try to run it basically anywhere, you're going to have these cold start times. What's the issue? We are an edge provider. We cannot afford 1.2 seconds cold starts. If we have that, that means that we can never shut down your website, which means that you can never save money, the money that we are aiming to save by using the edge, right? So we presented about a few months ago Instaboot. And with that, we are close to bringing cold start times to 0. So basically, how Instaboot works is we snapshot the whole state of the WebAssembly application into a journal. This journal has all the state of system calls that are executed prior doing the snapshot, which basically let us recover the program exactly at the same state. Even if it opened a socket, even if it opened a file or whatever, we recover the program at exactly the same point. Not sure if you have used Docker snapshots before, so it's something very similar, but way more optimized and performant. Why? Because in Docker, you need to snapshot the whole memory, even if it's not used, because the allocation is not linear. So that's one of the uniqueness things that we can do in WebAssembly that could be not done before. So thanks to all that, we achieved about 90 milliseconds cold starts. Here you have the QR code. If you want to read more about that, this will link to the blog post on how we make this possible. We don't have a lot of time, so I just cannot go in depth. So I want to finish just by how everything was plugged into production and how everything works in Wasm. So by the way, you can deploy WordPress from your phone. Here is one example of deploying a WordPress page just from Wasm. You will see here basically what are all the things that are happening. By the way, we are running jobs using the WP CLI, which is normal to use on WordPress. We are using Bash for actually executing the scripts. So basically in Wasm, you can run everything that you would need to run on the normal cloud provider, but now you can run it on the edge performantly and so on. So basically after around 20 seconds, we have the website live. The screenshot takes a tiny bit to generate. We are optimizing this. But here you can see the WordPress site is live. And yeah, this is how long it takes to actually deploy a website. And what's a cool fact? Everything that we presented today is now actually used in production. So right now you will have the very fast startup times. You will have the very fast startup times, and Instaboot is part of the pro mode for Wasm. So, but you will have very fast runtime and fast startup times if you need so. So that means that you can have your WordPress site live for the whole month and pay only when it's accessed. So that means you don't need to actually pay for the whole month. Maybe if your website is having 10 visits or 100 or 1,000 per month, basically you can actually use the free service. So yeah, I put the QR code. If anyone wants to try it, you can do it from your phone as well. So yeah, that's it about the presentation. Here you can find our handles. Edo doesn't have any handle on X or Twitter or however you want to name it. So if you want to chat right now, probably is the best time. And yeah, hopefully you have enjoyed our talk today. Thank you.
Do you have time for questions?
Yeah. Any questions?
What's the difference between
Boot.
Instaboot.
Instaboot and the Wiser?
Wiser.
How
So basically, Wiser snapshots the state just prior executing the main function, the start function. So it's a snapshot just before executing the start. So that means like if you open a socket or do things before startup, which by the way, this is super normal in Python, it's super normal in PHP. So for example, in PHP, you want to open a server. Like after executing the main function, you want to open a server, you want to execute some request to warm up your snapshot. In Wiser, you cannot do that. So basically, Wiser only snapshots the memory, and basically like what's the layout, kind of like, what's the layout of the WebAssembly program prior to snapshotting. In the case of Wasm, it goes one step further, and it snapshots the system calls that have happen before the snapshotting. So that means that you can recover your program in the middle of the program running, while Wiser is only at the beginning, if that makes sense.
So you mentioned snapshotting earlier, so I assume you mean Linux kernel snapshotting. So are you using Crew to do this? Or
No, we are not actually using WebAssembly Linux snapshotting. Other thing that is kind of like important to know is Wiser actually generates a new WebAssembly file. So this might actually like make the WebAssembly file a little bit bigger because the data needs to be shifted. In the case of Wasmer Instaboot, we generate a journal file with a snapshot. So you don't we are not modifying the WebAssembly file. In the case of Wiser, it's doing that.
Yeah.
why you went for extra ref instead of the more standard exception? The V1 dot something.
The legacy, the so-called legacy. I don't know why it's called legacy. It was the only name. I mean, if you even look at the proposal itself, the old non-xnref one is under the folder legacy. So I'm not sure how used it is in practice. But I guess the objective was to to start with, it was just a choice. We had to decide between one and the other. And we knew that V8, for example, had both. It supports both. And we just thought that xnref was gaining a bit more momentum and was actually the way that the proposal is to actually be accepted and implemented in the wider space of WebAssembly in general. I mean, what I mean is, I'm not sure if the legacy implementation will actually be implemented by any other new runtime. Will it be implemented? Go ahead.
I would assume, it's available in all browsers, so I would assume it's somehow, I don't know. I was wondering whether there's the,
I think that the... I don't think there is a difference between how LLVM, in the end of the pipeline, thinks about xnref and legacy, in the sense that it only has landing pads for what it's worth, what concerns LLVM. I think that the xnref, I'm glad to stand corrected, is actually the evolution of the legacy. It's the new way, the new proposal that the legacy mechanism is to be implemented. So yeah, that's it, I guess.
Yeah, in a nutshell, basically like we future-proof Wasmer. Otherwise, basically like we'll need to re-implement it twice. One for legacy and the other for the new one. So at the end, it was like we want to save time. And we already could prototype the other.
I think there was another question.
Thank you for the presentation. I have two questions regarding Instaboot. Could you please talk a little bit what state goes into the snapshot? So you have like globals and linear memory. I don't know, Wasmer doesn't support fuzzy GC, but another state and tables. Is it all preserved in the snapshot? And another question is, at what point the snapshot can be taken? Like when a call to Wasm completes, or is it at any point? Thanks.
So basically, the first question was about. Can you repeat the first one?
What kind of state goes into the snapshot?
Okay. So basically, we save everything. We save the globals. We save the data. We save the system calls that happened. We save literally everything. It makes things a little bit challenging because, for example, when you want to open a socket, the operating system will not give you the same FD that you're using. So it makes things snapshotting. We are using other technologies to actually like compact the journal, what we call like the snapshot, to be able to, let's say, like you write multiple times into a file, and this can be compacted, then we'll compact it so to make it only one call. So we are doing certain things small to try to accelerate the snapshotting when we recover from it. But in general, we save the whole state. And regarding the second question, which is where can you snapshot? The answer is anywhere. Anywhere. There is only one catch. The catch is right now for snapshotting to work universally. We actually are doing that specific part through Asyncify. The main reason for this is because even though like it only slows down certain parts of the code, not the whole, just kind of like when we snapshot and so on, it makes it usable on the browsers and on the servers in exactly the same way. There is a way to actually make this super fast, extremely fast natively, but we could not assure the same thing on the browser. So currently, like we are using Asyncify to make it universal, but the truth is this can be actually done extremely performantly without the 2x slowdown from Asyncify using LLVM stack points. So basically, like based on that, you have your program executing, you can save the state at any moment. You can save it actually multiple times if you want, and then the program will recover exactly at the same point. Inside of a loop function, if you want, like basically like just anywhere.
So currently it uses Asyncify, so all the caveats apply. So you have slower, after Asyncify is applied, you have slower code, you have larger binary. Also, I think Asyncify has a number of issues, like if your function returns some Wasm GC types, it can't work. It doesn't support hibernating inside cache of the exceptions. So
Yeah. The cool side is right now, unless you want to make it work with indirect calls, the cool thing is actually like you know what functions are going to be snapshotting. So actually you only pay the overhead on those functions that might be calling the snapshot. So that means that like actually you can get this run extremely performant. Why? Because normally, like you want the snapshots to happen on the main, happen on a certain part that you know actually like when it's going to happen, like more or less at compile time. So it's at the end like you don't pay as much as you were paying when asyncifying the whole module and everything needs to be asyncified. You still pay some price. So for example, we are doing that when we are forking the process on Wasm. And the main reason for this is there is no more performant way of doing this on the browser. But either way, actually, like on the server, when we are on control of our own compiler and the code that we emit, we can actually like just be extremely performant there. We have not just walked that path yet, but yeah, it can be possible.
thank you.
You're welcome.
Just sorry, curiosity on this snapshotting. Would not be possible to ship the asyncified function twice, one in the asyncified version and one in the regular version, where you say, yeah, you're out of it and you get some.
Fun fact for Clang, we actually got Clang compiled and running on the browser about 4 months ago. I don't know, 4 months ago. And actually, we are using that exact strategy because LLVM was huge. It's like, I don't know, like 15 megabytes or no, it was 90. I don't know, it was very big. So basically, like, I think if I had a module that big, actually makes sometimes crash. So we actually had to make that the strategy on, like, just asyncify this certain path, but not the whole. And we have, like, 2 Clangs. One is the asyncified one, and the other that is not asyncified. Because Clang just kind of, like, forgets the process and calls itself. Any other questions? Cool, perfect. Thank you very much.
Thank you.
Thank you.